Hello everyone, welcome back. So you have been gone through the complete series for the machine learning. Today we'll be covering the deep learning. We'll be starting this series, and let me start with very simple that what even is deep learning. Okay, so here's a best analogy for it. Think about that you are learning to recognize a cat as a kid. Okay, now nobody handles you a rule book. You just saw enough cats. First, you notice edges and colors, and then sharpness in the body parts, and then the whole animal. Your brain will ultimately understand layer by layer that this is a cat. Okay, so that's how exactly deep learning works. It take raw data, pixel, words, audios, and learn presenting automatically layer by layer without any manual programming the rules. Okay, now how is it different from the classical machine learning? So we have a comparison between two. In classical machine learning model, like decision tree, SVM, you have to manually figure out that which features matter. You basically tell the model that hey, look at these specific features, they are very important to be get into account. In deep learning the model figures it out itself. Okay, but when it comes to trade off, classical ML works greater with the small data set and give you interpretable results. You can actually understand that why it has made that decision. Deep learning need a massive amount of data, required powerful GPUs, and it's largely a black box. Okay, so you often can't explain that why this happened. In machine learning, this is your best friend for structure and tabular data. Deep learning shines on the images, text, audio, video, and the multimodal scenarios. So moving forward, the deep in the deep learning. So this just refer to the number of layers in a neural network, not how you have handled the problem. Moreover, that abstract representation, which mean that how better a performance can be done on complex task. So moving forward towards section 2, the artificial neuron activation function and the neural architecture. All right, so what we are going to cover in this is that first of all start with the artificial neural. A neural takes in a bunch of input, multiply each by the weight, basically that how important the input is, add them up all up, through in a bias terms to shift things around, and then passes the result through an activation function. Mathematically that's just z equals to w transpose x plus b, and then equal to f of z. Okay, now the activation functions are critical. Here's why. Without them, no matter that how many layer you have in the stack, the entire network collapse into a single linear transformation. It basically useless for anything complex. Activation function introduces non-linearity. That is why it let you the network lean, curved, complex, and real world pattern. The most common one are ReLU, used in hidden layers, and surely simples. It value is negative and the output is zero. Otherwise, it pass it through fast and very efficient. Second one is the sigmoid. It squashes between 0 and 1, used at the output layer for binary classification. Third part is Softmax. Use the output for multi-class classification. Convert your raw data stored into probability that add up to 1. Fourth part is the Tanh, used in the older network and RNNs, and this is similar to Sigmoid, but the output is between -1 and 1. Okay, so let's now zoom out to the full network architecture. A standard feed-forward network, also called as multi-layer perceptron (MLP), has three parts: the input layer, receive your raw data; second, the hidden layer, that is where the learning happens. Each layer learn increasingly abstract feature. Third part is the output layer. It spit out your final prediction. Okay, so moving forward towards the section 3, that is the gradient back proportion, gradient descent, and the loss part. So let's start that how we can go through this. How so network made a prediction and how does it work if it is wrong, and how does it fix it. Okay, so step 1 is that we measure the error using the loss function. For regression problem, we use the mean squared error, basically the average of square difference between the prediction and the actual value. For classification, we use the cross entropy loss, which measure that how far your prediction is from the probability of the true label. Step 2 is the backpropagation. This is the magic behind the training. Once we know that the loss, we work backward through the network following a chain rule from calculus, computing that how much each weight contribute to the error. Think of it like tracing blame. The weight in the layer 3 caused 30% of the mistake, so the weight in the layer cost 20%, and so on. Okay. Third part is the gradient descent. Now we actually fixes the weight. We nudge every weight slightly in the direction that reduces the loss. The size of that nudge is controllable by a learning rate, the single most important hyperparameter in the deep learning. Okay, so too large to learn a model having a learning rate, then your model can explode also. So in practice we use adam and rms prompt. These are some of the adaptive optimizers that we can use. We have already previously talked about it. Moving forward to one of the most important part, that is overfitting and how to fight it. Okay, so overfitting is when basically your model memorizes the training data instead of just genuinely learning from it. It performed great on the training examples but completely fail on new and unseen data. Here are some of the things that how you can fight it with that. First one is the dropout. During training, you just randomly switch off a percentage of neurons. This forces the neural network not to highly rely on every single path. Second is the L2 regularization or the ridge regularization that we have also talked. You add a penalty to the loss function based on how large the weights are. This discourages the model from assigning too much importance to any single feature. Third part is the batch normalization. After every layer, you normalize the output so that they have a consistent scale. This stabilizes this training, speed things up significantly, and act as a mild regularization. Step 4 is early stopping. You monitor your validation loss through training. The moment it stop improving, you stop training simply but incredibly effectively. Fourth part is the data augmentation, that you artificially expand your training dataset by applying transforming, flipping images, rotating them, and adding noise to it. Then, moreover, we have splitting your data into training, validation, and the test set. That you have the test set once at the very end. In the section 5, we'll be discovering about some of the major architecture and some of the final touch to that. So mlp, that's a feed forward network, the most basic architecture, that is fully connected layer, works well for the tabular data and the regression task. Second one is the cnn, convolutional neural network. They go to for any of the visualization. Instead of full layer connection, cnn used to share convolution filter that slide across images looking at the pattern. Third part is the RNN and the LSTM. So it's a recurrent neural network designed for sequential data. They maintain a hidden state that act like memory. So previous input influence the future output. Great for the time series speech and the old NLP task. Moving forward, we have the transformer, the king of modern AI power, GPT, BERT, translation system. We'll also be covering a paper on attention is all you need, and I'll be giving a paper analysis for that also in upcoming lectures. Then we have the autoencoder. So it learned to compress data down to small bottleneck representations and then reconstruct it. This is used for compression, denoising, and the generative task. Then we have GAN, that is very important, generative additive network. So there are two network fight each other, a generator that try to create a fake data and a discriminator that try to catch it out. Okay, so all right, that's about a basic intro about deep learning. So with this, we'll be having some of the key points for that. The deep learning learns hierarchical representation automatically. No manual feature engineering is needed in that. Second, networks are built from the neurons, doing weight sum following up by nonlinear activation. Third part is backpropagation and gradient descent is how the network learn by minimizing a loss function. Fourth, that a learning rate is most critical hyperparameter. We use Adam as your default optimizer. Fifth, that overfitting is a central challenge. Fight it with dropout, regularization, and batch normalization, early stop, and more data. Sixth part is different architecture. CNN, RNN, transformer are built for the different type of datas. Seventh is that always split your data into training, test, and validation. This will be see that how we can split it to get a better evaluation. Okay, so with this we have covered the complete basics of deep learning, that how what is deep learning and how it work. In the upcoming lecture we will be covering some of the projects related to this, and in a new series also we will be covering about some of the paper analysis that are very important for the deep learning. Thank you.